Okay, so we are looking at the process of generating proofs in first order logic, and in particular we are looking at this process of forward chaining. We started by looking at this rule called modified modus ponens. So, let us begin with that. And let us define it formally. So, what we are saying here is that if you are given a formula alpha implies beta, which is an implicit quantifier form, and for the moment we are working only with universally quantified statements. And if you are given a formula delta, then you can infer a formula, let us say gamma. So, from this and this infer gamma, if one can find a substitution theta such that alpha theta is equal to delta. In this notation, what we are saying is that we have applied the substitution theta to the formula alpha essentially. So, wherever the variables that are talked about in theta are present in alpha, we have substituted them with the whatever the substitution specifies essentially. So, if we can find a substitution theta such that when we apply it to alpha, that formula alpha theta becomes equal to this formula delta, then we are in a position to apply modus ponens. And what do we infer? We infer a formula gamma, which is obtained by applying the same substitution to beta essentially. So, this is theta applied to beta, and in the first case it is theta applied to alpha essentially. So, this is a modified modus ponens rule essentially. It actually combines two steps of first order logic. One is the step of universal instantiation and the second is the step of modus ponens. It does everything in one step, but the thing is that you have to find this theta on the way essentially. Why is it called chaining? Because let us say you are given a fact alpha and you have a rule which let us say is in the same form, is alpha implies beta. So, you can now infer from this beta by applying modus ponens, and if you have a rule of the form beta implies gamma, then you can infer from this gamma, and if you have a rule of the form gamma implies let us say delta, then you can infer delta essentially. So, what are we doing? We are in some sense chaining the rules together. And since we are doing it in the forward direction, that we are moving from what is given to us or what the facts are and moving towards the conclusions, this process is called forward chaining essentially. And we will start by looking at this algorithms for forward chaining. This theta unifies in this example alpha and delta. So, if you apply in this case of course, delta may not have had the variable in the example that we were looking at, but it is possible that that delta also may have had the variable. So, theta is a substitution which unifies two or more formulas. In this case there are two formulas, and when we say unifies, we say make identical. Essentially, and the algorithm which we will look at today is the algorithm which will find this theta essentially. So, theta is also called the unifier or a substitution, but basically a unifier and a substitution are the same things essentially. So, let us first talk about what are we going to look for in this algorithm. We want to look for something which is called the most general unifier, often known as a MGU essentially. So, let us understand first what do we mean by most general unifier. There is a more general than relation. Relation between formulas. We say that alpha is more general than beta if there exists a substitution or a unifier. Let us use this term theta such that you apply theta to alpha and you get beta. So, if you are taking a formula which has a universally quantified variable and you are substituting something for that variable, you get a new formula beta. Now, obviously, this alpha is more general than beta because it is talking about a universally quantified variable, but in our example that we have been looking at, we are substituting man x with man Socrates. So, obviously, man x is more general than Socrates, and this is the formal definition of more general than essentially. So, let us look at an example to understand what are we talking about when we talk about most general unifiers and why are we interested in them essentially. So, let us say that we are given two facts. The first fact is that on or rather above So, the first thing you must of course get used to is to read this statement as a universally quantified statement. Both x and y are universally quantified variables, which means implicitly there is for all x for all y sitting out there, but of course, since we are using the implicit quantifier form, we are not writing that essentially, but you should read this as saying that for all x for all y, and above or below are two variables which between us we will understand them to be the fact that when we say above x y, we mean x is above y and below y x means y is below x essentially. So, this statement is essentially saying that for all x and all y, if x is above y, it means y is below x essentially, that is all we are saying here essentially. And the other statement that is given to us is, let us say above Z flow. Again this is a universally quantified statement. It is saying that everything is above the floor essentially. Now, notice that when we write floor we did not put a question mark. So, it is not a variable, whereas Z we put a question mark. So, it is a variable. So, that is a convention that we will follow essentially. Now, you can see that here is a case where we can apply modus ponens and we can make an inference that below floor table. So, we can infer. So, given these two statements, we can infer that the floor is below the table. How do we infer that? We use a substitution theta, which says that you must substitute. I will not write the question marks here, because it is clear that it is a variable, or let us put it just to for the sake of consistency. I can substitute a constant table for x. I am allowed to do that, because universal instantiation says you can substitute anything actually. Likewise, I will substitute for z the word table, and I will substitute for y flow. So, observe that this substitution is a unifier. For these two formulas above x y and above So, it unifies these formulas, the left hand side of the implication and the other statement that are given to us, which means it makes them the same, and then we can apply this substitution to the right hand side according to the modified modus ponens rule, and substitute for y we will substitute floor, and for x we will substitute table, and we will infer that the floor is below the table. So, it is a perfectly valid inference to make essentially. But we could have chosen another substitution as well. So, let me draw this in a different color here, and this substitution says, so let us call it delta. This says that for x I will substitute z, and for y I will substitute floor. I am allowed to do that. Remember that you are allowed to substitute a variable with anything, you can even substitute it with another variable essentially, it is the same thing essentially. So, from this I will infer below floor z. Just apply the modus ponens, modified modus ponens rules, apply the substitution theta, and you have produced a new inference. This says that the floor is below everything else essentially. So, observe that the second this thing is more general. Than this one essentially, right. We have made two inferences, one of them is more general than the other essentially. Why is it nice to make more general inferences, because you can always apply the universal instantiation rule. I can apply u I here and get the other inference essentially. So, it makes sense to make more general inferences than less general ones. If I am told that everything is above the floor, I can infer that the floor is below everything else essentially. And then of course, I can go on to infer that the floor is below the table, the floor is below the fan, the floor is below the chair, and all kinds of things I can infer essentially. And you can see that below floor everything is more general than below floor table, because when I substitute table with the variable z with table, I will get this new formula. So, this notion of more general than holds between these two formulas and this thing. So, we generally extend the notion of seeking more general inferences to most general inferences, because essentially we are saying that the more general the inference you can make, the better for you essentially. So, make the most general inference that you can make, and the substitution which allows you to make the most general inference is called the most general unifier. Okay. So, in this example, this is the MGU, and we are interested in an algorithm which will allow us to find the most general unifier, and this algorithm is a very well known algorithm called unification algorithm. It is a kind of a central to theorem proving in general or logical reasoning in general. I have not defined what is meaning of most general, but you know that given in any partial order or given any lattice, when you have a ordering which says that more general, you can easily define what is most general and so on and so forth. So, something is most general if there is nothing which is more general than that. So, we will not define this here essentially, but I expect that you have accepted the notion of most general unifier, and we are looking at an algorithm for doing that. So, only for this algorithm, I want to also introduce this different way of writing formulas, which is you can find in this book by Charniak and McDermott, which I mentioned. The book is called Artificial Intelligence, and they use what is a list notation for writing the same logic formulas. It is nice to use list notation, because when you are writing programs, they are easier to process as compared to the mathematical notation that FOL uses essentially. So, in this list notation, this statement for all x man x implies mortal x, which has become our favorite statement, will be represented as follows. And I will just use this illustration to and you can work out what this list notation works essentially. So, for the first thing is that the connectives are not infixed, that they are prefixed, they come before the two operands, and secondly, we do not use any special symbols like the connective symbols we are using or the quantifier symbols we are using. Instead, we would write this formula as we use for all, and then we give the variable name, that is a quantified variable. Then we start the scope of the quantifier. In this example, that is the rest of the formula. Then we first write the connective, and we use this notation if, because since we are familiar with that. So, let me use lower case. Then we begin a bracket to put the left hand side. This left hand side can have any nested formula inside. Okay. In this example, it is man x, but let me just add a different thing. So, man x and uh, let us say just for argument's sake tall x implies mortal x. So, essentially we are saying all tall men are mortal essentially. Maybe we are not saying anything about short men here, mind you, we are just saying that if x is a man and x is tall, then x is mortal. Just to illustrate this list notation. So, now I have to put the antecedent of the implication. The antecedent is a conjunct. So, I first start by writing the connective, then my first argument to AND is man x, which also I write in list notation. So, I put the predicate symbol also inside the list, and the first argument in the first element in the list is always the important thing. It is either a predicate or a function or a connective. That if you keep in mind, then you will remember this. The next argument to this is tall x, then I close the bracket to say that I finish with the AND part. Now, I write the then part in some sense. We do not write then, because that if is enough to identify that, we write mortal and the appropriate number of brackets. Now, that is always the problem with list notation, to figure out how many brackets you need. So, let us hope this is correct, maybe we need one more bracket or something like that. So, only for this algorithm sake we will use this notation, but in practice of course, if you are writing programs to do the reasoning, then you can see that this notation is simpler to handle than the mathematical notation, which will require special treatment to different kinds of things. Here everything is a list essentially. So, the unification algorithm that we will look at, we will just look at two lists essentially, and in the implicit quantifier form we simply throw away this part and we put a question mark wherever the case may be. So, that is simple essentially. So, we are only left with this if and statement and so on and so forth. So, for the sake of this algorithm, we will distinguish between variables So, we will assume that we have a way of testing that it is a variable, constants, and lists. So, for the sake of unification, remember what the unification is supposed to do is to take two formulas or two expressions and find the substitution which will make them the equal. We do not particularly care that it is a logical connective or it is a predicate name or it is a function name, it does not really matter, because we are just now interested in making the two expressions equal essentially. And the only thing we are allowed to do is that we are allowed to substitute variables with something else, that is the only thing we are allowed to do essentially. So, if I had to let us say if I was given this fact that if and man Socrates, tall Socrates, I do not know whether he was tall or not, but let us assume that he was tall, then my goal is to unify this formula, sorry, to unify the left hand side, which is this, which the left hand. Okay, so I am not given that this thing. If I am given the sentence that all tall men are mortal, which in implicit quantifier form is the first sentence in blue, and the second sentence which is that Socrates is a tall man, which is in the sentence in the red, then if I can unify the underlying parts, then I can apply the modified modus ponens rules to infer the right hand side essentially. Now, as far as unification algorithm concerned, we just want to treat variables and constants and lists separately essentially. So, I will just give an outline now and I hope you will work out the details. The basic idea behind the algorithm is to scan left to right the two formulas or the two expressions that are given to us, trying to unify them piecewise in a recursive manner essentially. So, of course, at the high level the argument will have something. So, the high level argument would be like this, that we would say unify pat 1 pat 2. So, this is the notation I am borrowing from Charniak and McDermott, where pat 1 and pat 2 refer to the two expressions or patterns that you are trying to make equal. The first thing you do is make a call to another. Okay, so, I should really use the proper notation here. So, this bracket should come here. So, if you have the algorithm called unify for pat 1 and pat 2, we call another algorithm called sub unify with pat 1, pat 2 and an empty list or empty set, if you would like to say. We include a third argument, and you must be familiar with this style of writing algorithms, where you include the third argument and you keep building up whatever you want to this thing. So, our idea is that the substitution will be stored here. So, we will essentially scan the two inputs pat 1 and pat 2 left to right. Left to right is only incidental, because typically algorithms have to do it in a deterministic way, and do one of the following: keep building up the substitution essentially. So, when we say pat 1 or pat 2, they will refer to these. They are either variables or they are lists, constants, or they are lists essentially. So, let us deal with the simpler parts first. When both are list, both pat 1 and pat 2 are list, I am not writing the details here, then recursively with the first element of the list, the second element of the list, the third element of the list, and so on essentially. So, in this example, that you can see that in fact, both the patterns that we are trying to unify, and man x tall x and man Socrates tall Socrates, these are both are lists. So, we will first try to unify and with and, then this sub list with this sub list, which will be done recursively, and this second sub list with the second sub list here essentially. So, if both are lists and both must be of the same length, which I have not written here, because you cannot unify two lists of different length, then you can unify them piecewise in a recursive fashion. So, call sub unify with the first one, then with the second one, then with the third one in this example, and at all stages keep augmenting the substitution that you are finding essentially. If it is constants, if both are constants, then they must be the same. So, we have only two kinds of things, either lists or constants or variables essentially. Variables are the ones which have question mark below them, and everything else is a constant essentially. So, and is a constant here in this two lists. So, they must be the same, and will match only an and. Man is a constant, it is a predicate as far as we are concerned, but as far as unification algorithm goes, it is a constant. So, man must match man exactly, tall must match tall. So, wherever they occur, they must be the same constant essentially. That leaves us with variables. So, I will just take a few minutes to talk about variables. So, unification. So, we are talking about sub unify, right? Pat 1, pat 2 and some theta that we have built up when this particular call to sub unify is being made essentially. So, we have dealt with constants and lists. Constants must be identical, lists must be of the same length and we will make recursive calls to the same sub unify. Now, we are left with the case where we have to deal with variables. So, case pat 1 and likewise I would say for pat 2, essentially if either of them is a variable. So, let us say when pat 1 is a variable, then we say call another function which is really doing the hard work. So, we will say where pat and theta. So, this is another subroutine that we are writing or sub module we are writing, in which the first argument is a variable, the second argument is a pattern and the third argument is the theta essentially. So, we have to look at a few cases here. If variable occurs in pat, return failure. I will just state it today. In the next class, we will look at an example and we will probably revisit the algorithm again essentially. So, if the variable occurs in pattern, which means somewhere inside the pattern it is there. Now, remember what we are trying to do is to eventually our goal is to be able to add our goal. Why do I keep doing this? Our goal is to eventually say that theta will become theta union where pat. If everything is fine, we will say substitute this pattern for this variable and then that is one step towards making the two formulas the same. So, that is the goal of this where unify module, that to substitute pat for variable, but we are putting in a check first. We are saying that if the variable occurs in pattern, then you cannot do this essentially. That is one check. You must think about this a little bit and we will see why this is the case. Then if variable pat 3, let me call it, belongs to theta. If variable already has a value in theta, then call sub unify with the pattern that you are trying to unify the variable with and this pattern that it already has a value. Try to see if you can make them the same If that is the case, then whatever the values returned by them will be the value that you will add to that essentially. So, if variable already has a substitution in theta, then see whether that substitution and this current pattern will match or not essentially. If you come through this, otherwise you simply say theta or return theta union this set. So, this is where really all the work is being done in the where unify this thing. It has these two tests before you can substitute the pattern for the variable, and it has been shown that this algorithm will return the most general unifier, which will make the least amount of substitutions to make the two input patterns identical essentially. And it has also been shown that the most general unifier for any two patterns is unique, which we will not go into here in the detail here essentially. So, in the next class when we meet, we will revisit this unification algorithm, and we will see examples of why these two particular tests have to be done before you can actually add the substitution.